Hi, welcome to the webinar of Ctype harmonic filters for arc furnace facilities. This webinar is brought to you by Encos and EasyPower. So we're going to look at the Ctype filter construction and how it works using EasyPower. My name is Pablo. I'm an electrical engineer from Mexico. And at Encos, we deal a lot with arc furnace facilities. So let's get started. Now, for those of you who don't know or are not very familiar with what is an arc furnace, it's the most modern way of making steel. An arc furnace is basically a huge short circuit in which the arc produced by the short circuit is so hot that it melts steel. So this is an electric arc furnace here in Mexico. This is about a 60-ton furnace. And as you can see, this is the shell of the furnace, this lower part in here. This thing extracts the fumes from the furnace. These are the electrodes, which are the ones that produce the electrical arc. These are made from graphite. This is like a crane. It's the arm of the furnace. This thing goes up and down along with the electrodes, allowing the arc to be near or far the scrap, which is inside the shell. Now, these huge cables, which you can see in here, are the main feeding source for the graphite electrodes. These are water-cooled cables, which have to be water-cooled because they carry huge currents, therefore they get very hot, and if it were not for the water cooling, they would melt. Now, behind this wall is the furnace transformer, which is a huge transformer, and we'll see it in a little while. Here you can see a little better the detail of the vault that contains the transformer. The transformer is in here. These are the cables that go from the transformer to the furnace. So this is a quite recent furnace. I think it's 6 or 7 years old. So how the furnace works: some scrap material goes into the shell like this. This is scrap steel, which can be found in any junkyard. And then the electrodes that can move up and can move down go very near the scrap metal, and since they have a voltage applied to them, they will form a short circuit, and that short circuit will form an arc, which can get very, very hot, around 20,000 degrees Celsius. So that arc starts to melt the scrap material, and it starts to form a little pool of molten steel, along with a little layer of slag, which is the result of all the impurities from the scrap steel. Let's say plastic, let's say other metals, whatever it is, starts floating on top of the molten steel. So as the melting process continues, the electrodes can go up or can go down depending on the part of the cycle. At the beginning, the electrodes have to be near the metal, and then as the metal starts to get molten, the electrodes can go up or can go down depending on the power that should be delivered or how much heat the furnace can resist. Now, as you can imagine, the scrap material inside the furnace is not at all organized. It's very disorganized and it's very random. Therefore, the electric arc that is produced in the furnace is very erratic, and it's a completely random phenomena. The correct word is stochastic, which is, it means that it's very chaotic. It cannot be predicted with a lot of certainty how the arc will form, what trajectory would it follow. So before continue, I want to show you a very brief, it's 2-minute long video of an electric arc furnace here in Mexico working. So this is 2 minutes long. There we have the furnace that is being filled with scrap. You may notice that there is a pool of molten steel already in there, and this is done not to let the furnace be completely empty. Besides, the heat from the molten steel helps to preheat the scrap and to eliminate some of the impurities of the scrap before the melting begins. You will see in some seconds that when the scrap falls, a lot of fire will turn out. This fire is due because the steel, since it is scrap steel, has a lot of grease, a lot of oil, and this burns instantly on contact with the already molten steel. So there goes the scrap. And all that fire that you see is not of the melting process. It's just the plastic, the oil, and the grease on the steel burning up. Now, you might see that the lid will come. It's like a pot. And the lid goes over the shell. You already can see the electrodes on the upper part of the furnace. They are totally up. Now the lid goes up the shell and it goes down, sealing the furnace. And now there's a very brave dude that works the oven. And now the melting process will begin. The electrodes will begin to lower and they will start to form the arc, which will in turn melt the scrap steel. This is done manually by an operator in the booth that I'm standing when I was recording the video. Now you can see the electrodes are going down and they will start melting shortly. Now that's the melting process. That is an electric arc. Now it may not seem so because of the video, because I'm in the operator booth and I'm behind the, I don't know, a 3 or 4 inch glass. But that process you're seeing is extremely noisy and it generates an extreme amount of heat. Being around the oven is very uncomfortable, but well, in the operator booth you can check it out. So that's the first part of the process is called boring, because the electrodes start going into the scrap. They penetrate the scrap, and as it starts to melt, the electrodes start to go up and a more stable arc is formed. So that's the video. Let's continue. Now, a typical system, an electrical system for an arc furnace is formed by a very robust utility. In Mexico, we have at least 115 kilovolts up to 400 kilovolts. I don't know in any other parts of the world, but these are Mexican voltages. They are very high voltages and they imply a very robust system, very stable line. It's dedicated to the steel mill. So the next thing we can find is generally a pair of transformers. One is intended for the electric arc furnace and it's a huge transformer, and right next to it you will find another transformer which is for the rolling mill. Now this transformer, the one for the electric arc furnace, is for the electric arc furnace which melts the steel. And then we have some ladle furnace. A ladle furnace is also an arc furnace, but much smaller, and the steel is refined in that furnace. It's not molten because it's already molten from here, but the steel is refined in the ladle furnace. They add oxygen, carbon, nitrogen, whatever it takes to make the desired steel with the desired properties. These transformers are typically 230, 34.5 kilovolts. This is a very typical arrangement in an electric arc furnace facility. Now, next to it, we'll have a much smaller transformer, which is 20 to 60 MVA. The electric arc furnace transformer typically goes from 60 to 120 MVA. It's very big. This one is much smaller, and it's for the rolling mill. It's just for the machines that will treat the already molten steel, the rolls of steel, the rolling to the desired width of the steel. Normally, this part of the plant is handled at 13.8 kilovolts, at least here in Mexico. So after the main reactor, the main transformer, we will find in some facilities this is quite optional. There are some facilities that have it, some that don't. But you will find that current limiting reactor, which is a huge reactor that is connected in series between the main transformer and the electric arc furnace. The purpose for this current limiting reactor is to stabilize the arc. It's an inductance, so it doesn't let the current change as abruptly. This reactor will have a voltage drop since it's a series element. Therefore, you'll have less available voltage at the furnace, therefore less power, but a much stable arc, which is desirable. This reactor is tapped. You can see that you can connect it in many positions. This reactor has 1, 2, 3, 4, 5 taps, depending on the operating conditions. Now, normally, when an electric arc furnace facility is designed, they do not know for certain how the furnace will operate. So they let the reactor to be changed to match the operating conditions, both actual and desired. So that's why it has taps. Now, when you get closer to the oven, I'm gonna go to my first picture. When you get to here, to the transformer that is exactly right behind the furnace, you will find a very specially designed transformer, which is an electric arc furnace transformer that can handle huge secondary currents, 10, 20 kilo amps, because it's a lot of power with a lot of very low voltage. So these transformers are specially designed because they are subjected to extreme mechanical, thermal, oh, there's a typo here, thermal, and electrical efforts. The voltage on the secondary of this transformer goes around 660 up to 1000 volts. This is a typical secondary. So you may find this very, very low in comparison to the main voltage for this transformer, which is 34.5 kV. So it's quite a difference in voltage, quite a difference in current. As you can notice, the secondary of this transformer connects to the oven not by cables but by copper buses, which are also water cooled. It's a lot of current. So as you can see, this is the main furnace transformer, which is up there in the substation. This is a 230 kilovolts to 34.5, and it's an 800 MVA, a very big transformer. And this is the rating for the electric arc furnace transformer, which you can see that it can operate from 43 MVAs up to 60. The range can vary quite a bit because depending on how high the arc is, the power of the furnace varies a lot. So it can vary from 43 to 60, quite a variation. And the low voltage can go from 600 volts to 990, almost 1000, and it depends on how high, how long you need the arc to be, and it depends on the part of the melting process that you're in. So this is a typical electric arc furnace transformer. Now, electrically speaking, the arc furnace is quite interesting because, as I told you before, it's a very stochastical, it's a very random process in which you have no certainty on how the furnace will behave, how much current precisely it will draw, and especially less what the harmonic spectrum will be. If you think of a motor, if you think of a drive, if you think of pretty much anything, you can know with a fair amount of certainty how that machine will work power quality wise, how the harmonic spectrum will be. In a furnace, you may have an idea, but it's very, very difficult, if not impossible, to estimate precisely. What it is known is that it varies a lot, and it varies depending on what part of the process, of the melting process you're in. When you start to drill, to bore in the scrap, the arc is very, very random because the scrap is in a random position. So harmonic content is high and it's very asymmetrical. When the steel is molten and you have a pool and the arc is a little more stable, you can estimate a little better how the arc will behave. But in the beginning, it's very, very hard on the system because it varies a lot. The power drawn varies a lot along with the current, and the harmonics are very unstable. Besides, an electric arc furnace is pretty much like a welding machine, a soldering machine, but huge. So the main, one of the main characteristics of the arc, it's that it's highly asymmetrical to respect of the x-axis, which means that even though, that's awful, which means that even though you have a high degree of distortion, there will, in a normal load, you can have symmetrical, an x-axis symmetry. But in an arc furnace, you can have a very asymmetrical load, which can be something like this. This has a high degree of asymmetry. When you have asymmetry on respect to the x-axis, you have second harmonic. Now, normally in a system, when you have second harmonic pollution, it means that something is very, very wrong. A transformer is saturated, some rectifiers are broken or about to broke, or you have some electrical discharge somewhere in the system, maybe partial, maybe full, maybe it's intentional because of an electric discharge device. But normally in electric systems, you do not have second harmonic or even harmonics for that purpose. Let's say 2, 4, 6 are harmonics that normally don't exist, but in an arc furnace, you do have a lot of second harmonic. Now, normally, when we have harmonic content in a system, the most popular and the cheapest solution is the notch filter solutions. When you want to filter a harmonic from a system, you may install a passive filter, which is the most popular and the cheapest way to free harmonic content from a system. And that filter will drain the harmonic, the tuned harmonic, to the ground. Let's say this is a fifth harmonic filter, which is very popular, fifth harmonic filter. All the fifth harmonic current will flow through here to the ground and will not dwell in the system. It will not cause distortion in the system impedance. Now, these filters are very good when you just want to filter 1 or 2 harmonics. But when you want to filter a lot of harmonics, especially in the lower end of the spectrum, let's say second or third harmonic, these filters present a very important problem where these filters, they don't eliminate resonance, they just displace it. Now, to see what I mean, let's go here on EasyPower. Ignore all of this. This is a very cheap, this is the furnace facility that I was showing you earlier. It's a 230 kilovolts utility. We have a large transformer for the arc furnace and the level furnace, and a smaller transformer for the rolling mill, which I really don't care about. And now we have the furnace transformer and the electric arc furnace. Don't mind this for now. As a matter of fact, I'm going to turn them off. And these are typical notch filters. How does a notch filter works? Let's try with a fifth harmonic filter. When I turn this filter on, when there are no filters, the system is mainly inductive. As frequency goes up, impedance goes up. Fairly basic. But when I add a fifth harmonic filter, let's say, how does the system respond? Now I get two important points. This is the resonance. This spike here is the resonance, which is a point that I want to avoid, completely avoid. And this is the anti-resonance, which is the point that my filter is tuned to. This is a fifth harmonic filter, and the anti-resonance is a little lower to avoid drawing much current, and there are other factors which I will not discuss in this webinar, but this is the anti-resonance. Now, you might see that the resonance doesn't disappear. It's still there, and it's a resonant point for the system, but it's not in the fifth harmonic. It's a little lower. Now, let's try the same thing with a seventh harmonic filter. The resonance doesn't disappear from the system. It's still there. It's just a little lower. And this is a resonance that I definitively want to avoid, because it's right in the fifth harmonic, which is a harmonic that you normally have a lot of content, a lot of fifth harmonic because of the drives. So this is not a good solution. Now, when I try and apply that solution to the third harmonic, let's say, I have a resonance right up in the second harmonic, which it would normally not be a problem. But as I told you before, in an electric arc furnace, I have a lot of second harmonic. And if I leave this filter here, it will produce a lot of distortion in the voltage. So a filter, a notch filter at least, more than a solution, becomes a problem, a huge problem, because of this resonance that is behind the tuned frequency. So in order to fight this condition, there's an implementation of second and third order filters, which can include a resistance in series with capacitance, or a combination, well, a parallel combination of resistance, inductance, and a series capacitance, and they attenuate the harmonic resonance. The problem with these filters is that they tend to have high losses at low frequencies, which is exactly the thing that I want it for. I want this kind of filters for low frequencies. So if I place one of these filters alongside a notch filter, which is this one, a notch filter on the same bus, a resonance is very, very likely to occur. So instead of solving the problem, I'm making the problem even worse. Now, if that's your wish, EasyPower does include the option to try notch filters, first order, second, and third order harmonic filters. But I'm going to show you a solution that is not included in EasyPower, but we can of course make it. And this goes to show the versatility and the power that EasyPower can really get you into. So the Ctype filter was a filter that was originally designed for HVDC systems. Now, this is not new. This is at least 30 or 40 years old, but it's not so common to hear about Ctype filters. Now, the thing about the Ctype filter is that it functions as many types of filters at once, and I'm going to show you why in just a few slides. Now, HVDC systems, because of how they work, the power electronics, tend to produce a lot of harmonics on both sides, on the AC and the DC. So many filters are required to provide a good power quality on the system. And as it turns out, this type of filter works great for electric arc furnace facilities because of the implied harmonics. So, what should be the objective of a filter? A filter should supply reactive power at fundamental frequency for power factor correction, which is what every capacitor and every filter does. Now, this is a plus. Losses should be minimal at power frequency and resonant frequency, or at least near the resonant frequency, which is a trouble that the second and the third order filters have. The losses tend to be high at low frequencies. So in order to save money and to reduce cost, losses should be minimal. And besides, resonance should be attenuated. Otherwise, a notch filter would work, but I don't think the notch filter is a solution. So this is a very important factor on the C-type filters. So some very, very clever fellows came up with this solution. And this is a C-type filter. You may seem that it's quite close to what EasyPower offers, let's say to the third order, which has a capacitor and a series combination of R and C and L, well, parallel L. But the C-type filter is different because what you have in series is not C and R, but C and L. This is called the tuning branch. This is the tuning branch. This is the main power capacitor, and this is a resistance. The attenuation comes from this resistance. So this filter works like this. At the fundamental frequency, which here in Mexico is 60 Hertz, maybe if you're in Europe, it's 50 Hertz. L and C, which are this branch, is tuned to be a short circuit. So at 60 Hertz, this branch is a short circuit. And then the only thing that you have, this is the bus, this is the main bus, is the bus, a short circuit from by these two, and the main power capacitor. So the voltage in this bus is exactly the same as the voltage in this bus. And then you have the resistance. And when you tune that filter, or when you analyze that filter from the tuned frequency, which is the frequency that you want to filter out from the system, the whole filter, which means L, C, and C1, the whole thing is tuned to be a short circuit, which is pretty much what a notch filter does to filter out that harmonic, to provide a path of minimum impedance from the bus to the common point for that particular harmonic. So these are the conditions that should be met. At fundamental frequency, L and C is a short circuit, so the only thing operating in the filter is C1. At the tuning frequency, the whole filter is a short circuit, so that harmonic is filtered. Now you will have, because it's a parallel circuit, some current going through the resistance, yes, of course, but the most current will go through this branch because it's a short circuit. Either at 60 Hertz, the reactive power will flow mainly through here. Some will go through here, yes, but mainly through here. And at the tuning frequency, this whole thing is a short circuit. So I'm not going to bore you with algebra. It has a lot of algebra implied, but and it's not hard. But I don't think that's the point of the webinar. So as you might see, at 60 Hertz, we want this impedance, well, reactance, and this reactance to be equal. So this is a short circuit. And then we have only this. The bus voltage since this is a short circuit, will appear in here. So it's very easy to estimate this capacitance if we know how much power we want to draw from the filter and the bus voltage. So XC1 is fairly easy to estimate along with C1. Now, through some circuit analysis, which I will not perform here, we can arrive at some equations which are very, very simple. And we should only have in mind how much power do we need from that filter, what's the system voltage, and what the tuning frequency will be. Usually, this type of filters are used for second harmonic. It's the most widespread use I've seen. So, no. There are some very easy formulas for C1. This is the main power capacitor. For C, let's say CS, it's the series branch, and the LS. These are some very, very simple formulas that can be programmed in an Excel. And then you have the design parameters of the filter, which are XC and XL. This is the tuning branch. Now, how much resistance you need depends on the Q factor. Q is the quality factor, which is about the bandwidth of the filter. So I'm going to tune this filter to the second harmonic with a quality factor of 2. Now, all the formulas are here. I want to create a 12 MVAR filter. So in EasyPower, and I think this is the interesting part of this webinar, I don't have the option to create a C-type filter, at least not for now. Maybe in the future, not for now. But EasyPower is so versatile and so powerful that I can build my own C-type filter. And it's a little bit of cheating. Actually, it's cheating, yes, but it works, so it's fine. This is my my C-type filter. Now, you're looking at the exact same thing here and here, although it may not seem so. This capacitor, C1, is the main power capacitor and is the one that's going to be producing the desired reactive power. And I have this capacitor here, 12 MVAR. Now, normally when you design a notch filter, the voltage here, the capacitor voltage, is much higher than the bus voltage because of the harmonic response from the inductor. In a C-type filter, because this is a short circuit, this voltage is the same as this one. So it's very easy to estimate the voltage for this capacitor. So I'm placing it at 13.8, which is the same bus voltage. Now, for creating the other elements of the C-type filter, which is the resistance, this capacitance, and this inductance, I'm going to use busway. And remember, this is a little bit of cheating, but it works. Now, busway allows me to enter impedance. Now, let's check it out. The inductive reactance, yes, this impedance, I got it from my Excel, and it's 5.29 ohms. Now, this is plus J. It's an imaginary part which is positive, as is any reactance. So I'm going to put that in here. In here, this is my inductance, and there we have the positive sequence reactance is 5.29 ohms per 100 feet. So to have this in ohms, I'm going to enter 100 feet. Now I'm going to use every inductor should have a little resistance. And I'm considering this is a very high quality inductor which has an X over R ratio of 100. So the resistance, the positive sequence resistance, is 100 times lower. It will have some losses as any real inductor, but these are low. This is very high quality. And for the zero sequence resistance and reactance, I'm going to use the smallest possible value that I can input in EasyPower because I don't want to consider those, not for now. This is the inductive part. It's this one, L. Now, this is the capacitive branch. Since in EasyPower I can only have capacitors in parallel, like this one, I cannot connect anything below the capacitor. I have to cheat a little and define, I'm going to use busway again. So, as you might remember from your circuits courses, capacitors have a negative reactance. So if I follow my formulas from the Excel sheet design, I will find that what I could have deducted from common sense, that the reactance should be the same, will appear, which means the formulas work. So I have this value for the capacitive branch, this one, the series capacitor that I'm going to tune the filter with. And I'm going to input this again 100 feet, and this is my capacitive reactance. Notice the minus sign because it's capacitive, minus. Now capacitors have very little losses, so I'm not gonna consider the losses of the capacitor, therefore the resistive part of the capacitor. And for the positive sequence and negative sequence resistance, it's a very small value, negligible. And the zero sequence reactance, also negligible. So I pretty much have the L, the Z, C, and the power capacitor. Now I'm only missing the resistance, which again comes from this Excel, and I'm going to input this value. That's it. It's pure resistance, no reactance. So let's see if it really works. When I make a power flow analysis, you may notice the voltage is a little low, doesn't matter. But the important thing is how the filter is working. Remember, this is a 12 MVAR filter, and it's producing 11.19 MVAR because the voltage is a little lower, which is fine, but it pretty much works exactly how I want, power-wise. Now, there are some very interesting things to notice. I'm going to check how the current is working in the branches. So you can see that most of the current is going through this branch, the one with the inductor and the capacitor. The branch with the resistance has very little current, so this resistance doesn't need to be very high rated in terms of power, in terms of current. It can be an economical resistance, so to speak. Most of the current goes through this branch, as expected. Now, another important thing is that this branch is acting pretty much like a notch filter. So the voltage for the capacitor, remember, this branch, this one in here, is a model of this capacitor. And check it out, the voltage is a little bit higher. So when you're designing your filter, you should take that into consideration. The capacitors for the tuning branch will have a fairly larger voltage depending on the harmonic, but it will be much higher than the power capacitor, which is not even at 1 pu. This one is at almost 1.3 pu. You should watch out for that. So much of the current is going through here. What about the power? we have a capacitor, well, yes, a capacitor that is outputting almost, well, let's say 11 MVARs. And most of that power is going through this branch. And then you may notice that we have an increase before the busway and after the busway, which means that it's working. So this is the power produced here. Then this capacitor, again, this branch represents this capacitor, is also producing power, of course. But when it comes to the inductive part of the filter, which is this one, this excess power, let's say, will be consumed by the inductance. Since this reactance and this reactance are the same and the current is the same, one will produce the same that the other one will consume. So in the end, what you have going into the system, it's 11 MVARs, which is the exact same number that got here. So whatever is going out of the capacitor goes here. And again, some of the power will flow through the resistance. This branch and this branch are in parallel. Therefore, the current will split. Necessarily, some power will flow through here. But in the end, this filter is producing in here for the system the exact same amount of MVARs that are coming out of the capacitor. 11.196 are going out of the capacitor and into the system. So power-wise, the filter works. Now, what is interesting is when we analyze it from the harmonic point of view, this load has a little harmonic content resembling an electric arc furnace. Again, it's very hard to predict how much harmonic you will have, but it's an estimation. You can estimate a worst case scenario, a best case scenario, whatever works for you. So right now, I think we have a lot of distortion on the bus, 5.24, which is quite high for such a high voltage bus. And let's see what happens if we apply, let's say, a third harmonic filter, a notch filter, which is the most typical solution. The distortion goes a little lower, yes, but when we have the fifth harmonic filter, check out the distortion. It will go high, and when the seventh harmonic, it will go higher, not a desirable trait. So what happens when I have the second harmonic filter? It goes down. Now let's see how the system behaves. For example, with the fifth harmonic filter, we have what it's expected, a resonance around the fourth harmonic, the anti-resonance a little below the fifth. And let's check it how our filter works. Now, this filter is working exactly as intended, because the resonance doesn't displace to the left. Because of the resistance, that resonance will attenuate very, very much. You can see that the system response is practically inductive. There's no resonance point, and that is important because that way the distortion goes way lower, especially for the second harmonic. Let's see what happens when we change the resistance. So we change the tuning factor, the quality factor. Let's say this is much higher, 70. Now the response of the filter starts to the resonance goes a little higher, and it still works fine. What happens when I add a lot more of resistance? Let's say the resonance goes higher, much higher, but in all, The filter works very well to attenuate the harmonics because the system is mainly inductive and the resonance is attenuated. Now, this value, I think, should be lower. Let's see. So the filter is working great. Now, what happens when I add the other filters? Let's say the third and the fifth harmonic. I have the resonance from the fifth harmonic filter, the resonance from the third, but on the second harmonic, which is the one I really care about in the arc furnace facility, I have no resonance. Therefore, I will not have second voltage harmonic distortion. And to make an example out of this, I'm gonna make a truly worst case scenario where I'm gonna place a lot of harmonic current just from the second harmonic, maybe 40 megawatt system, let's say 20. So in all, it's a lot of harmonic current. So when I make the summation, I find that I have quite a lot of distortion. And another way to see if the filter is working is to check out the current that it is drawing. The second harmonic filter is just drawing, well, it's mainly drawing second harmonic current. So it's working as intended. It's providing a lot of reactive power, it's filtering the second harmonic, and it's attenuating the resonance. Now, these type of filters are recommended for lower order harmonics where notch filters don't work out so well. And the main use is second harmonic, yes. So, I guess that's it. So, okay. If you have any questions, as always, please, well, this webinar comes from a really great paper, which is the theory for the design of Ctype filters by these three fine engineers. Also, the golden standard for power quality in power systems, which is the 519. And if you have any questions, please feel free. Well, thank you, EasyPower, so much. Please feel free to email me. I will answer you back as fast as I can. So, well, thank you very much for everything. I hope you liked the webinar, and I guess that's it.